Hi everyone, welcome to part D of my video series on discovering novel strategies to defeat COVID-19 through knowledge graphs. In part A of this video series, I gave you an introduction as to why I feel knowledge graphs will be helpful in tackling COVID-19. In part B, we had a discussion of the existing knowledge graphs and the limitations thereof. In part C, we discussed the challenges in creating a universal COVID-19 knowledge graph to address the limitations of the existing knowledge graphs. And in part D, I'm going to illustrate how we can create knowledge graphs using manually curated data. So one of the things which I discussed in the last part C, was that given the complexity of extracting the source, target, and relationship triplets from the research papers using scripts, uh, given the accuracy, given the low accuracy that was seen, particularly in extracting relationships, and given the limited time we have, given the seriousness of the situation, I decided to go for manual curation of data. But because the number of research papers is pretty huge, that is for something I'll require help from you all. And what I'm trying to illustrate in this part, in part D, is once we have the curated data set, how we can make use of this curated data set to plot the graphs. Now, the graphs which I plot here are plotted using the NetworkX module of Python. In the actual application, they'll be plotted differently because in the actual application, you'll have a different interface. Here, I'll just show you a Google Colab interface. However, the focus in this video will be more towards describing the functionality, towards describing what are the different options that can be made available and how will they be made available in the UX, in the actual application. That's a different discussion, which is part of another video. So I mentioned I curated a couple of research papers. So there were three of them that I'm listing here. The first research paper which I curated, the data set for, was shielding and beyond the role of glycans in SARS-CoV-2 spike protein. I'm also mentioning the COVID WHO ID for that. So as I'll discuss in my future videos, when you go to the WHO COVID website, you get a database for all these research papers. Let me illustrate here only. So you will go to research paper for WHO available on WHO website, and you'll have this COVID-19 database. When you go to this database, for most papers, you see a COVID WHO. For all the papers, you have a COVID WHO link. So this is a COVID WHO ID. This is the ID which I'm populating here. This is kind of used to uniquely refer to the research papers. And what also I have shown is the different data sets. So the data set for each of these research papers that I've curated. So this paper, Shielding and Beyond, is already open with me here. This is a pretty extensive document, pretty extensive paper. It is also biologically intensive. So it's not something, say, slightly generic. It's not something generic like, more generic like medical management of COVID-19 evidence and experience. The first paper has to do with spike protein in particular. Spike protein has a central role in COVID-19 infection, as you might know. So let me open the three papers first, then I'll open the respective curated data sets. So this is the second paper, medical management of COVID-19 evidence and experience. I'll open the PDF of it. The PDF is loaded. And then you have the third paper, drug targets for COVID-19, ongoing global efforts. Yes. So again, let me go to, so this is the first time I'm opening this link. So the link for curated data set for this paper. And while how I curated and what are the things to be kept in mind in curation is up that discussion is a part of a separate video. That's part of uh, part E of the video series. However, I'll just mention here briefly that whatever important information is present in these research papers, uh, say COVID-19 is caused by this virus, for which the short form is this, and the antibody development efforts are focusing around spike protein and what is the function of the spike protein, how does it do that function, and you have what are the features of spike protein, what does it use those features for. So all this information is captured here. I have the COVID WHO ID as the title of the research paper. This uniquely identifies the research paper. And then I have all the information which I just discussed. The causative virus for the disease, the full form of the virus, what do the antibody development efforts, what are those where they revolve around, and what are the features of the spike protein, what is its function, what is the function of glycogen shield that the spike protein has, and so on. So similarly, if I go to the second research paper, the curated dataset for the second research paper, that is medical management. Again, let me, yes, scroll down. They're talking about COVID-19 disease, the causative virus. So this is something which you will find in a good number of research papers. They're talking about WHO, they're talking about remdesivir receiving emergency use authorization, etc. So this is something which I'm mentioning here. COVID-19, the full form causative virus, and about remdesivir receiving authorization, and where it originated, where COVID-19 originated. So that is something that is discussed here. It originated in China, in Wuhan, in China. When did it originate? So all those things are mentioned here. So this is again because the document is pretty extensive. This curation is pretty extensive. Going to the last link, which was on drug targets for COVID-19 therapeutics, ongoing global efforts. When I open the curated dataset for it, let me open that. Let me put the paper against this dataset for easier reference. And you see, this dataset is about, again, starts with COVID-19 and SARS-CoV-2, but then it comes down, it comes to the different things which it talks about is, it talks about other diseases like SARS and MERS, Middle East Respiratory Syndrome, and it talks about the comparison between SARS and SARS-CoV, as in SARS and COVID-19. It talks about the different classification. It talks about the classes of coronaviruses, the structure of coronaviruses, the classes of coronaviruses, alpha, beta, gamma, delta coronaviruses. So all this thing is something which I have described here. So the SARS, MERS, the structure form of coronaviruses, what are the different kinds of coronaviruses that you have there, and where are they found in. So all the information which is captured in this research paper, the information which actually is kind of not so fast changing. So I do not report, for example, the number of cases that may have been found in a particular area, because that information is subject to change. So of course, one won't keep it as part of the curated data set. I'm taking out, I'm extracting, I'm leaving out the figures and extracting the other information, the information having to do with biology, information having to do with genes, chemicals, drugs, other environmental factors that may be making an impact on the virus, and so on, that may be an impact, may be making an impact on the disease, and so on. So that's the idea. In my next slide, I'm going to show you the code which is being used to plot knowledge graphs based on this curated data set. And in this code, there will be different options. So this code is meant to explain what different things we can do with this curated data set, some of the things which we can do with this curated data set. And particularly I have illustrated functions as to how we can fetch all the nodes connected to a given node from a data set. How can we plot a knowledge graph for that? How can we plot a subgraph, the entire subgraph which is connected to a particular node? How we can fetch a particular relationship through different edges. So these are things which I'll be explaining in the code. Let me go to the code itself. It will be easier that way. So this is my code. This code is written in Google Colab. So when I'll execute the functions, when I'll plot the graphs, it'll be plotted in Colab. This will be different from the actual application, which will be for which the interface will be in Vue.js, as I'll discuss later in I think in part E of my video series. So let me first connect to Google Colab. This will locate the VM, and so in the first step, I'll be importing the libraries, the modules. So all my data, the COVID-19 research data that I've curated, that is present in my GitHub repository, which you can download from. If you wanted to, this code is available there. The slides will be shared with you. So you can go and download this. In this function, I'm just collating the different data sets and including the references. So each node occurs in a particular paper. It is important each entity, be it SARS-CoV-2 or be it say heparin or say spike protein, they occur in a particular research paper, in one or more research papers, and somebody may be interested in seeing which research papers these terms are occurring in. So I'm just collating this data. I'm implementing a logic whereby I can link as to which research papers a particular term is present in, and I'm removing the unique rows. So as you saw in the beginning, you have some basic information like the full form of SARS-CoV-2, the causative virus of COVID-19 that is present in multiple research papers. So those duplicate rows are being removed, the unique rows are being kept. Let me execute this function. So in my GitHub repository, if I were to show you the structure, so I have a file, I have a main folder COVID-19 in which I have other subfolders. So if I go to COVID-19, and do an analyst on top of it, so I have two folders. One is of curated dataset, other is of sample files. So the sample files contains random files, which I use for experimental purpose. This curated dataset actually contains the curated information of different research papers. And this, if I check the present working directory, so this is here, this is content COVID-19. So here this will be content COVID-19, and you'll have curated data set for this if I were to go inside that. So I needn't have done it, I could have seen it from here only, correct. So this is the link in which all my research papers are present. I'm passing that folder link to this function. So my corpus is generated, corona corpus is generated. If I were to just see what it looks like, so it has 1193 rows, close to 1200 rows, and this is starting from this research paper, shielding and beyond. And you would see two kinds of relationships. So here you have the data coming from the research paper as such, coming from the document as such, and then for another research paper, these two research papers are different. You have references to nodes, references to entities, references to targets, and as to which research paper they are in. So there'll be obviously intermediary nodes and intermediary information in between. So this is from 4 and this is to 302, and there'll be information after this. But what I like to emphasize is that in order to be able to see which node is contained in which research paper or papers, I have this relationship explicitly mentioned for all the nodes. So that is not something which you mentioned when you curate this data set. Of course, that will be too repetitive and inefficient. That is something that is taken care when the code is implemented. Uh, Next, I have a function of plot to plot any knowledge graph that I may be interested in. And here I have different functions. So if I want to generate the entire knowledge graph related to a corpus, or if I wanted to generate the subgraph around a particular node, or if I want to see the relationship, what is the relationship a particular node has, so how to which other node a given node is connected with a particular relationship, as I'll illustrate in a few minutes from now, a function for that. I have another function for knowing which nodes are connected to different depths to a given node. And in each of these, I'm giving the corpus as a reference. So as I show, I'll be passing the corona corpus as the first element, as the first parameter. The second is the node that I'm interested in. And then if I'm interested in depth, I'm passing depth as a parameter. If I'm interested in relation as a parameter. And then there is this fourth parameter or third parameter, the last parameter, which is one of reference. It's either true or false. If you select it as false, you don't get the references as to where which research paper those notes are occurring in. If you select it as true, you do get those references. So a person may be interested in knowing whichever nodes are connected to a given node, which research papers those nodes are occurring in, so that he can go and refer to the research paper himself or herself. So that option is there. To start with, so I have already jotted down certain options here that I'll be executing, certain so functions, the parameters with which I'll be executing the functions. And if you remember in video 2, in part B of the series, I mentioned explicitly that these knowledge graphs actually don't, the existing knowledge graphs don't actually focus on the possible strategy to tackle COVID-19. So while different researchers in their research papers would have referred to one or the other approaches, but that is not something with which the knowledge graphs start from. The different existing knowledge graphs start from, or that is leave aside starting from, that is not even one of the elements of those research of those knowledge graphs. So however, in my knowledge graph, I do have a separate node for possible strategy against COVID-19. And let me see which all nodes are directly connected to it. So which are the possible strategies to tackle COVID-19? So depth-based subgraph. Oh, I'm sorry, I haven't actually defined this. I haven't actually executed it. So if I want to see all the possible strategies against COVID-19, I'll just execute it, and I have 3 papers. I think from each paper I got something, or maybe from 2 papers I got these 3 strategies. So as they mentioned, one strategy is that we can focus on disruption of dimerization in sp9. Another strategy is we can focus on the glycation shield of SARS-CoV-2 as protein head, and I think this is not. Oh, I can, of course, I should be scrolling it. I see. So this is, the length is smaller here. I'll have to actually change it. Maybe I'll increase it to something like 40. Here again, it is smaller. Let me actually set it bigger. I'll set it to 60 this time. When this experiments actually, we will have to expand these nodes and then see. So what is the reference there? So one of the possible strategy against COVID-19 is that we can make use of agents that modify the pH or inhibit proteases endosomal cytine protease, and these two proteases TMPR SS2 and TMPR SS11D. Another strategy is that we can go for disruption of dimerization in sp9, and another strategy is that we can exploit the vulnerabilities of the glycation shield of SARS-CoV-2 as protein head. So it was to get to this that I had to actually expand it, and I think that that format generally works, so I'll be switching back to it. Uh, the initial thing which I had, I think it was 30. So in this case, we didn't really have many nodes, but if you have many nodes and you want to actually see them closer to one another, it will be helpful to reduce the size. So if I increase the size, then nodes, these edges will actually stretch out unnecessarily. So if I want to see all the nodes which are connected to each of these three strategies, my initial focus was on possible strategy against COVID-19. So you have a disruption of dimerization in sp9 that is linked to an sp9. You have this, and it is linked to different topics. So it is linked to these two entities and to this process. I'm talking about vulnerabilities of the glycation shield, so of spike protein head. So this is referring to spike as protein head, and you have further attributes. So this is referring to glycation shield, and then there is another relationship that so this is actually camouflaging of head is insufficient for particularly for large probe radii, which is being referred to. So similarly, I can go away further, depth further, to see which relationships these are further linked to. So what will happen in that case is uh, each node will further expand. But for an sp9, for example, I'll be able to see better graphs. I'll be able to see the relationship, further relationship for that. So you have this possible strategy against COVID-19. You have disruption of dimerization in sp9, and this is linked to actually a dimeric form of an sp9. So this relationship is one for an sp9. Let me expand this further to make it more explicit. So you have possible strategy against COVID-19. One strategy is inhibiting viral infection through disruption of dimerization in sp9. This is linked to NSP9, so actually that is getting overwritten through some other node. And this NSP9 is, what is this NSP9? This is RNA binding protein. What is the attribute of it? It has a dimeric form. All these are described here. Now, the confusion occurs because you have so many nodes, particularly when you go to depth 3, and it will be difficult to visualize. However, in the actual implementation, you will not have all these nodes coming together. You'll be able to click on a particular node and see the further relationships for yourself. Suppose I was interested in knowing the different research papers in which these nodes are occurring in. I can simply make it true, and I'll first restrict myself to a depth of 2. So as I mentioned earlier, for each of the entities here, for the target entities, I have a research paper attribute, a research paper relationship, and as you can see here, uh, in possible threats against COVID-19, all the nodes which are connected, for those nodes, I'm showing which research paper they are a part of. So this is COVID WHO 617295, and this is COVID WHO 614382. So different nodes are part of different research papers. And suppose I wanted to see what are the names of those research papers. So one way is to actually change this to 3. So this will be further expanded. As of now, this is just 2. If you change the depth, even this node will be further expanded, but I think that will be too much because anyway it's pretty huge. You can use another function which is a relationship, generate relationship, relation link, whereby you can mention the name of uh, the COVID WHO ID and this relationship, and then you will be just able to see what node is that, what research paper is that. So again, for this, I wouldn't require an area that was, so this is here, it's long, here it's small. Okay, so I'll tweak that once again. I'll tweak the width once again. This works differently for different visualizations. So some visualizations are better viewed when they are more compact, more compactly represented. When I increase the width, this node is unnecessarily getting increased in length. So the research paper title for this was Shielding and Beyond the Role of Glycans in SARS-CoV-2 Spike Protein. I do not actually need this much of length, but this will actually in the actual code, these lengths will be something which will be lesser, and they'll be based depending on the scenario that I'm interested in. So here, because to start with, I standardized it to display different graphs. This seems to have created a problem, and now depending on the graph which I'm trying to display, and depending on the details that I'm interested in, I'm having to go back and recheck it and redo it. So here again, I'll be showing the references, and I'll be showing. So I think I did it. Possible strategy against COVID-19 3. Okay, so what I did before was I checked up to a depth of 3, but there I had the false option enabled, so I wasn't interested in looking at the references. But if in case I was interested through this approach, so what I'll get will be a pretty dense graph, because this will contain all relationships which those research papers have. Well, let me execute it nevertheless. This took a while because it is enabling the references, and this is not usable except in the real implementation, where you'll not see all nodes at a time in one node, which you can click on and expand to further nodes. However, why this is coming in this form is I have the option true enabled here. So what this option true does, it links to the research paper name, and then from that research paper, whichever other nodes are present, it links them as well. So if I were just to restrict it to say false, as I did earlier, I wouldn't have this problem. So the number of nodes would still be large, but because I'm not explicitly referring to any research paper title here, that comes in when I have actually the option enabled is true. So this is reduced. So generally I keep the option as false, except where I actually need to see which all nodes belong to which paper. And there is another function which is easier for that, and that is the generate relation link, which I discussed a minute or two before. Let's move to something else. So very quickly, I would take a real example where I would show how we can see the information about hydroxychloroquine. So this was touted as a potential drug to tackle COVID-19. So if you want to see the attributes of this drug, the different attributes related to this drug, you see them here. So what is the effectiveness, what are the pros, what are the possible adverse effects, how does it function, what is the proposed dose, and well, so this, some notes are occurring multiple times because there may be one possible adverse effect, there may be one possible uh, uh, pros, and so on for cons. So this is because the way I have actually listed down these entities is I've tried to maintain uniqueness in each node. So I'm not in pros, I'm not just listing it all pros at once, because the important thing is actually to break it down into different nodes so that these nodes can be further connected to other nodes. So that is something which I'll illustrate in the next step, where I'll actually change this to have this change to U to 2, and this will further expand. So, all right. So all those nodes where I had, which were connected to, directly connected to hydrochloroquine, they are expanded now. And as you can see, when you expand those nodes, you're able to see other relationships. So if this shows that the possible adverse effects of hydrochloroquine is hypoglycemia, then there is another node which shows that there is another link which shows that something else like chloroquine, which has the same adverse effect. And similarly for pros and cons, you have references to chloroquine and so on. So the point is, suppose here's a possible adverse effect. If it were a pros like here, and you knew that hydrochloroquine is kind of effective, you wanted to check which other drug could be effective as well, in case hydrochloroquine were not to prove successful, and which other drugs you wanted to test. So this would be a good way of building the relationship. You would immediately be able to know that uh, chloroquine can be tested or vice versa. Similarly, if I expand it to 3 to get further relationships, uh, the nodes further extend. And here again, the visualization is relatively complex because the space is less. What you'll have, what is expected to be in the real implementation, is you'll be able to click on a node and expand it or contract it as required. And as you can see, with each relationship, like say, this is referring to SLE, this is referring to system, the full form of this is systemic lungs uh, thamylosis. This is further connected back to hydrochloroquine, and you have other nodes which are actually which have more than depth 3. So by using by changing the depth parameter, we will be able to see which different nodes are connected to a given node up to a certain depth. So this, I believe, is quite useful. I mean, you can do it for spike protein, for example. Suppose you're interested in the properties of spike protein, or say you are interested in the properties of remdesivir. Let me try with remdesivir. This was another drug which was, I think, even now, I'm not sure what's the status on this as of now, but people were touting remdesivir as another potential treatment for COVID-19. Perhaps Trump was referring to it frequently. So this is remdesivir, the different attributes of remdesivir, and you would, I believe, of course, as you see here, you have direct links and then you have indirect links. So, for example, you have a link like, let me explain further. That remdesivir has certain attributes. However, some of those attributes are shared by another drug, leponavir-ritonavir combination, which can be used to serve those very aspects in place of remdesivir. Again, this drug has its own properties, has its own mechanism of action, has its own side effects, which one will be able to see when one goes through those notes. So again, the point is, you wanted to search information on remdesivir, you got it. However, you also were able to see which all drugs are similar to remdesivir in certain aspects. Uh, this was because I had actually put the depth as 3. If I restrict the depth to 1, I shall be able to get that. The immediate nodes which are connected to it. So this is much cleaner. These are the immediate nodes which are connected to it. And when you make it, if you were to make it to 2, each of those nodes would further expand. Yes. So this depth-based subgraph is an important feature whereby you could connect to any node. You could see all the nodes connected to a given node and further expand on those connected nodes to see further nodes. So starting with distance 1, 2, 3, and so on, you can go to different levels. Here, because I'm using the networkx Python function, I wouldn't be able to click on a particular node and to expand or contract it. I've just tried to show how by tweaking the parameter in the function, we can actually expand the number of nodes which are displayed. So I can connect to further nodes further down the chain. Another function is if suppose I want to be able to see the entire subgraph around a particular node. Suppose I want to see the entire subgraph around uh, a drug known as Obane. So Obane is a drug which, let me Google anyway. This is a toxic compound obtained from certain trees, which is used as a very rapid cardiac stimulant. It's a polycyclic glycoside. So this would be used in some. So this is a drug which is certain use, and I believe this was occurring in one of the research papers, so I just had it here. And if you wanted to see the entire subgraph around this particular drug, all the possible nodes connected to it without specifying any depth, this shows up. So you have Ubin, you have its mechanism of action, you have its pros, you have its cons. So within the mechanism of action, what are the attributes what are the further nodes which are connected to it? So this is a smaller graph because you have not many relationships related to it. But suppose it was something like spike protein, you would really have many nodes in the graph. I'm taking another drug which is tacrolimus. So I think this is an immunosuppressive drug. Yes, this is an immunosuppressant, and it is used for I think it's used in cases of organ transplanting, and this is something which is discussed, I think, in this research paper, drug targets for COVID-19 therapeutics, where they talk about how COVID-19 cases in patients with other problems like organ transplant or other complications are being tackled with. So that's how these drugs come into reference here. So you have tacrolimus, and you see different relationships which this drug has, the different nodes connected to it. Uh, Again, a very quick observation is that whatever this has, this is also served by another drug which is cyclosporin. So this shows all the nodes connected to this particular subgraph. Again, some of this information is not fully, it is, I think it's, oh no, not so fully displayed, so I'll have to change it, which I'm not trying to do right now, because anyway, I think you know what that would lead to. I mean, that only the information would get expanded. I would be able to see the entire thing. So there is a third function, generated relation link, which, as I described earlier when I was describing how you would be able to see the research paper name. So you can use this function to specify, suppose you want to see a particular relationship for a particular node. You want to see what are the pros of remdesivir, or you wanted to see what is the topological classification of spike as protein. then you could just mention the node and the relationship that you're interested in, and that relationship would show up. So all this shows is the process of remdesivir. Or suppose you were to execute the other node, this would show you the topological classification of the spike protein. So it has a tail, it has a head, and it has a stalk. And say if you were to go to some other graph, you would be able to expand. If I were to go to the depth-based graph, I would be able to expand these relationships further. So in this uh, collab sheet, through the medium of this collab sheet, through the medium of these graphs, I've tried to demonstrate how we can actually make use of a curated data set to plot different relationships. And as I mentioned earlier, uh, because of the fact that because of the requirement that we have to interlink the information contained in different research papers, to which knowledge for which knowledge graphs is a very good option. I plotted knowledge graphs here to actually demonstrate how this is done. So once you are trying to see the nodes connected to a particular entity, and when you expand on those nodes to different depths, you are able to see which other entities are related to it, and you may not have been able to know it by yourself. You may not know it by yourself. So relationships like hydroxychloroquine and chloroquine, or remdesivir and leponavir or ritonavir are actually similar in some aspects. Those relationships are not always very explicit. Of course, people who are involved in this research uh, know that, but then there would be plenty of other relationships which would come into notice once these knowledge graphs are actually plotted. So hope you like this. I think uh, it would have been awesome if there was a standard representation for the widths. So if there was a standard with width length which I could use, but what happens is if for example, increase the width to say something like 120, I make it really large, and then I plot it. Then I'll have to once again plot on each of these graphs further. So suppose now you want to see how it looks like. So the width, the length will be extended, but then these will not be clear. So that was something which I had to strike a compromise on. However, I believed that we did have a great insight into how these things are working, and what all uses can they be put to. So in this video, I have demonstrated you the different data sets that I've curated, and the knowledge graphs which I've been able to plot using those data sets. Again, there are many more functions which can be used for plotting knowledge graphs, and there are plenty more functionalities which I'm not illustrating here. If you were to, for example, search network X functions, you would see plenty more functions. So these are different functions. These are more functions which can be made use of. My objective is to say that whatever has been illustrated is the tip of the iceberg. Many more things can be done with the knowledge graphs. And depending, here I'm using network X. If I were to use another uh, implementation, if I wasn't doing it in Python, if I was doing it in say Neo4j, there would be a different feature. So however, the greater emphasis is on the very usefulness of knowledge graphs, that when you have knowledge graphs, you are better able to interlink relationships and discover new insights. And I believe discovering such new insights will go a long way in resolving COVID-19 problem. So hope you enjoyed the video. I look forward to meeting you in my next video. Thanks.